Welcome to AP Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at our Thermodynamics Lab. Now, I've broken the lab into really several different parts. There's the pre-lab portion, there's the portion around graphing and what you need to do in Excel for that, and then there's the final calculation portion. So if you need any help in a certain area, just move forward. Now, what we're looking at in the Thermodynamics Lab, it's really a Hess's Law lab. And if you take a look at the three reactions that are listed here, you'll see that if we take the first reaction and we flip the second reaction and add, we get the third reaction. So by Hess's law, 1 plus the opposite of 2 equals 3. That means the delta H of 1 plus the opposite of the delta H of 2. So we're going to multiply it by -1. If we reverse the reaction, that's going to flip the sign in the enthalpy, should equal the delta H of number 3. And that's what we're going to do in the lab. We're going to actually calculate the enthalpy per mole of reaction 1, the enthalpy per mole of reaction 2, and the enthalpy per mole of reaction 3. And we're going to see if indeed 1 plus the opposite of 2 really does equal 3. So big picture, that's what we're going to be doing in the lab. Now, in the lab, we're going to use a coffee cup calorimeter setup like you see here. So you take the lid off and that whole top assembly comes off, and we've got two nested styrofoam cups. We use two to try and decrease the amount of heat transfer between the surroundings and our reaction. And it's got a lid, and you'll notice it has a stir. You just slide that up and down gently, and that will agitate and stir very well the reaction mixture that we put inside the calorimeter. And then we've got a thermometer. So basically one person will hold the thermometer and the coffee cup setup, and then with the other hand, they'll move up and down the stir. And when the other person calls time, you'll tell them what the temperature is on the thermometer. And make sure you use the thermometer right. It reads the nearest degree, so you should be recording to a tenth of a degree with the thermometers we're using. Now, we're going to try and do three things to make maybe a better look at enthalpy in reactions than maybe you did in first year chemistry, honors chemistry, where you did a fairly simple coffee cup calorimeter type lab. Well, one, we're going to use a better calorimeter, two nested coffee cups with a lid and a better stirring implement. Two, we're going to try and account for the fact that when you put energy into the water inside this solution, some of that energy also goes into the coffee cup. And while in first year chemistry we assume that that is negligible, the reality is it's not negligible. And we can actually calibrate our coffee cup calorimeter, find its heat capacity, to actually find out how much energy it's taking over the course of the reaction so we can make our energy measurements better. So those are a few of the things that we're going to do here. We're going to use a better calorimeter. We're going to account for the fact that we are losing some energy into the coffee cup. And then finally, you found the delta, or I should say the temperature last year by just looking for the highest temperature. And we can do better than that. So there's really three different things we're going to end up doing to try and make this better. Now, finding the heat capacity of the calorimeter is really why we're doing part one of the lab. You're going to calibrate your calorimeter, determine its heat capacity. The basic idea here is if you look at the first sentence, let's assume that, and let me walk this down. So let me back out a second here. Do this in a way that we can kind of walk through what it is we're actually going to be talking about here. So let's assume that into our coffee cup calorimeter we put 50 milliliters of room temp water and record its temperature. And then we get hot water, and right before we dump it in there, we take the 50 milliliters of hot water, record its temperature, and we get the fact that the room temp water was at 25 degrees Celsius and the hot water was 65 degrees Celsius. And I know I didn't measure the temperatures right, but I'm doing this for simple math. So if you really think about it, 50 milliliters of 25 degrees Celsius water and 50 milliliters of 65 degrees Celsius water, when we mix those together, shouldn't the temperature end up at 45? So as the mixtures mix and we reach temperature equilibrium here, so the temperature equalizes throughout the entire solution with stirring, you'd think it's 45 degrees Celsius. But what if we actually measured it at 43 degrees Celsius? What happened to those missing 2 degrees Celsius? And that's really what we're going to use to calibrate our calorimeter. So let's say that we have a missing 2 degrees Celsius. We can use Q equals mc delta T. We know the mass of the water. That's 100.0 milliliters. We can use the density of water to 1.00 for pure water grams per milliliter to find its mass. We know the specific heat of water. And we've got this missing 2 degrees. We can calculate the energy involved in that missing 2 degrees. Well, that's the energy that went into the calorimeter rather than warming up the cool water. So we actually can measure then over that temperature range from 25 degrees Celsius up to 43 degrees Celsius, how much energy was stolen. And if we take that energy and divide it by that temperature difference, the difference between 43 and 25, we can calculate the heat capacity of that calorimeter. For every degree Celsius, how much energy does the calorimeter actually take? So that's really what we're doing in part one. Now in part two, what we're going to be doing is, oh, and about part one, you'll notice the data table here. This is the data table we're filling in. Just a couple of quick reminders. First of all, we've got 50 milliliters water at room temp, 50 milliliters that we're heating up. The room temp water, that's what we're going to call the initial temperature. So T initial that it talks about in the lab, that's our initial temperature in the calorimeter. And we measure the temperature of the hot water right before we dump it in. And then over time, we're going to record at different times what the temperature is. But the stuff down here at the bottom, remember, that's not data in the lab. These are values that are going to come from the calculations section. So the T mix and the T average and the others that are here, remember, that actually comes from the lab itself. And remember, if it talks about T average, that would be the average of these two. Because remember, we can take the average and we can see what the temperature should have been. And when we find our T mix, we can actually see what the average really was. And you'll notice it's going to be less. We lost some energy. Well, that's because it went into the calorimeter. Now, in part two, what we're really going to be doing is our three chemical reactions. So you're actually going to carry out reaction 1, 2, and 3 inside your coffee cup calorimeter and measure those values. So that's what we're going to be doing really in part two of the lab. Now, some reminders about pre-lab stuff. So things you should know for doing this lab. Well, one, we're not going to use the stir bar and the fume hood setup that it shows inside the lab in part four. Well, one, we don't have enough stir bars and stir plates for everybody to use the stir, so we're going to use that plunging up and down ring that does a good job of stirring. In the last section, we've got the lab ventilation on, and most people don't even notice that in that last step that there's some gases that are given off that could potentially bother you. So don't stick your face down really close and inhale deeply. And we're not going to use the distilled water. We're just going to use room temp tap water that I set out in a large carboy for you to use in the lab. Next thing, pour carefully. When you're pouring from a beaker into a graduated cylinder, the beaker is going to have a spout here on the end. And if you take and you set that spout right on our graduated cylinder and get the end of the spout really close to the end of the graduated cylinder and actually touch it onto the glass there, you should be able to carefully pour the liquid in without spilling. If you hold it above, or if you hold it so that the spout is too far over here, there's cohesive forces between the liquid that's in there and the glass. And when you pour slowly, it's going to stick to the glass, run around, and pour all over the place. So remember, sit the tip of that beaker right on the edge, and if you tip carefully, it should pour straight in. And when you're done, untip, and then move it across, lift up, and you shouldn't get any drops of water that come out. Otherwise, you're going to make all kinds of messes. And be very, 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 very careful to avoid contamination in this lab. Dispose of all your waste solutions down the drain, rinse with tap water from the faucet, and wipe it dry with a paper towel in between. So your calorimeter, as well as if you're getting your solutions in beakers, do that every single time to avoid contamination and to get as good of data as possible. You don't want any water left in there in this particular case. From the common drawers, you're going to get the 50 milliliter graduated cylinder, so you don't need to get that from anywhere. You leave all the ones that are on the center table in the area that's designated in the center table. If nothing moves from the center table with the fume hood, we don't get any contamination. So be really, really, really careful about contamination. But you're going to need to go over and get 75 milliliters of the room temp water to heat up to the temperature they describe in the lab. So you're going to need your graduated cylinder from the communal drawers. And once you've measured your 50 milliliters of hot water and you've dumped it in your calorimeter and started part one, put the 50 milliliter graduated away. And when you get your hot water, if you're uncomfortable with the temperature of the water and you're worried about getting burned, remember you can use the communal drawers from the beaker or the beaker tongs from the communal drawers and then just put them back away when you're done as well. Now from your actual drawer, really all you need is a couple of beakers. Make sure they're clean and dry. So when you get your liquids, because it's easier to get them in the beakers, bring them back, pour what you're supposed to pour inside the calorimeter, measure its temperature, and then right before you pour the other one in, measure its temperature and record those in your data table. but clean those beakers in between all of your steps. Now, the next thing is actually about the pre-lab questions that you've got to do for this lab. So just some reminders about the pre-lab questions. First is find the purpose. Remember to include in the purpose the fact that we're talking about a specific reaction. So we're going to try and show Hess's law using the reaction between ammonium and hydrochloric acid, ammonia and hydrochloric acid. Now, first thing, for pre-lab question number 3, when we actually get into the mass, or the math in the pre-lab questions. Remember what we're going to be using in pre-lab question number 3 is equation 4 from the lab sheet, our old Q equals MC delta T. So it's the mass of solution, specific heat of solution, temperature change of the solution. And look closely in the problem, you'll notice it gives us two temperatures from which we can calculate delta T. Always do that final minus initial. It mentions what our specific heat is, and it gives us the two volumes of the liquids, which we can add together to get our total volume of the water solution. And it also gives us the density that we can use to calculate what that mass would be. So we're not measuring mass directly, we're measuring volumes and using density to calculate our masses. And then we can calculate the Q of the solution. But remember, number 3, they asked for the Q of the reaction. And the Q of the solution is going to be the opposite in energy of the Q of the reaction. Now, when we get to the next pre-lab question, number 4, remember there that equation number 5 is really what we want to use. Because what we're trying to do is we could do this old calculation and get a look at what the Q of the reaction is. That's exactly what we did up here. So remember, before we multiplied it by -1, that's what that's talking about. But we can get a better look if we know the heat capacity of our calorimeter and account for the energy that the calorimeter stole. That would be this calculation here. So we add those two values together, and then that would be the total energy that went into the calorimeter and into the water. Multiply that by -1, and we get a better look at what the Q of the reaction is. And equation number 6 reminds us how we calculate that Q-cal. You take the delta T over which the calorimeter, so the initial temperature up to our final temperature, that would be the delta T of the calorimeter as well as the solution, and multiply it by the heat capacity of the calorimeter, which is given in the problem. And that will give you the Q of the calorimeter. And don't forget, round appropriately in each of these. So follow sig fig rules. And since we're using subsequent calculations, the answer here for there, don't forget to use the unrounded value. I know it should be rounded in the end to correct sig figs, but don't forget to use your unrounded value in your intermediate steps. And that's going to be something that applies in the last one as well. So for pre-lab number 5, what they want you to do is calculate kilojoules per mole of our product. Exact same thing we're going to end up doing in the lab. In fact, these are all calculations from the lab. Now, in number 4, you just found the Q of the reaction, but it's not in kilojoules. It was actually going to be in joules. So that's how we get our energy for the kilojoule part. And now to get our mole part, well, we just use some stoichiometry and look at what information we're given for the reaction. So they actually tell us in number 3 that we had 25 milliliters, or 25.0 milliliters to be exact, of our solution A, or mixture A. And it tells us in number 5 that its concentration was 0.60 molar. Well, we can use that to predict how many moles of A we started with. Well, we had the right amount of B, and notice it's a 1-to-1-to-1 stoichiometry. So if we can calculate our moles of A, then we also know our moles of AB. And if you want your energy in kilojoules per mole, get kilojoules, get moles, divide. And that's what we're going to do in the last pre-lab question. So if all you're looking for is help with pre-lab stuff, you're done. Next idea here. You need to understand that in this lab, we're going to be taking our data and we're going to try and find as accurately as we can what the instantaneous mixing temperature is. So it's not just go stick a thermometer in there and stir it and what's the highest temperature you get. We can do much better than that if we're careful. But we are going to end up graphing in number 1 of our calculations. We're going to need to do 4 graphs. And we're going to graph time versus temperature. Time on the x-axis, temperature on the y-axis. Now, when you go to do that type of graph, now remember, at the beginning, we've got liquid sitting inside the calorimeter, and it's going to be a constant temperature. So at the initial part here, we're not going to be changing temperature. Now, once we dump the other substance in, we're going to end up with a reaction occurring. And think of this on a particle level. So there's the physical mixture, and then there are the chemical reactions that happen in part 2. But it's all the same thing. When you mix the things together, inside it's going to react in different spots of the solution in different places as the chemicals come together, and that's going to release energy. So all of them don't react at once. And different spots of the solution, we're going to have different concentrations, different amounts of energy being released. And instantaneously, we don't reach a temperature equilibrium. So the temperature doesn't spread out instantaneously, and all the reactions don't happen instantaneously. So it takes a period of time for all these things to slowly start reacting, and then eventually it's all reacted. And at that point, if all of that went into water, we'd reach our highest temperature. So what we end up seeing typically is this type of thing at the beginning here. Is as the reactions start to occur and release energy, we start to warm up. And then eventually we reach temperature equilibrium, and then from there, we get this gradual cool down. Now, it's also possible that we may have our thermometer in a spot here where it was reacting a lot. So the thermometer was right here, and you may spike a high temperature. So you may be above that line as well. Well, we can end up with a good look at what the instantaneous mixing temperature is by using this portion of our graph. So that's really what we're going to be doing in an Excel graph or any other graphic program you want to use. And you have to analyze your points to see if there's anything that we want to end up dropping here, because we want to get to the point where we've reached our highest temperature and then we go through our gradual cool down. And if we extrapolate back and find our y-intercept, then we get our instantaneous mixing temperature. So we can't measure this directly, but we can theoretically figure it out through extrapolation with the data in our lab. So what you're going to end up doing is you're going to plot your data, and it's going to end up looking something like this. So you can see here that we've got a plot of our data points, and we've drawn a best fit line through those data points. And I've had it over here give us the y equals mx plus b. So you need to ask it to your graphing program to draw the best fit and then display the equation of the line. Now in Excel, you're going to basically right click on a data point and then add a trend line. And then in the options, you're going to say display the trend line on the graph. That's how you end up getting this. But one thing you need to recognize, two parts of this. One, over here, you'll notice there doesn't seem to be any 20-second temperature reading. Well, that was because when I did an evaluation of the data, I saw that at the 20-second mark, we had a low temperature. And it clearly wasn't into that cooling phase that we're going to be graphing to work back and get our y-intercept, our instantaneous mixing temperature. So I decided that that data point would basically drop my slope and negatively affect my instantaneous mixing temperature. So I decided to take it out of my data. Now, if I jump back, I think I had a data table back here somewhere. I want to remind you of something. If in your lab you decide to get rid of this data point, I want you to circle it and tell me that this data point was dropped in your actual data table so I know what you ended up doing. So don't forget to do that in your original data table. So in this particular case, that data point would have been low, would have artificially depressed my T-mix, so I decided to drop it from my data. So that's where the 20-second went, is I dropped it from my data, and that's going to give me a better T-mix. Now remember, my y-intercept in my y equals mx plus b form of my line over here is really what I'm looking for, and that's my T-mix. But you need to recognize something. Excel doesn't care about measurements and significant digits and proper accuracy and precision in calculated data. So you need to account for that. If you think about a thermometer ends up being read to the nearest tenths. So we shouldn't use 33.15 as our T-mix. We would say it's going to be 33.2. That would be our best look at what our instantaneous mixing temperature is if that was our data that we got from the lab and then it graphed out in this way. And remember, in your graph, you need to have the labels axes with appropriate units. You need to have an appropriate data or heading or why can't I think of the basic word for showing the actual name of the graph? So don't forget up here to include the temperature versus time label. So make sure you have your axes labeled and make sure you label the graph appropriately. And you have to use those words. They just need to be descriptive. And then finally, don't forget to show your y equals mx plus b. And that rounded to tenths. So our T-mix temperature over here, our y-intercept rounded to tenths, is going to be what we put back in our data table for T-mix. So that is my mention about the graph. Now that we've got our graphs, we get all of our T-mixes, we can actually get into doing our calculations to prove Hess's law. So number 2, calculate the average temperature. Well, we got two temperatures, the hot and the cold, they're the room temperature. Take the average of those two and you get T average. Now number 3, you're going to use the difference between those two. That's our missing temperature that we're going to use in our Q equals MC delta T calculation. And remember, we don't know the mass of the water, so we have to use the density of water as 1.00 grams per milliliter to take our volume total inside our calorimeter of our water and use that to calculate our mass of our water here. And then specific heat of water is given, 4.18 is what they're telling us to use. And remember, delta T would be T mix minus T average. That's going to give us our missing temperature. And remember, the heat gained by the calorimeter is equal to that lost by the water, but opposite in sign. So don't forget to appropriately go from one to the other. And then the last one here, number 4, calculate the heat capacity of the calorimeter. Well, we just calculated our Q of the calorimeter. That's what we did up there, because this calculation is going to give us the Q of the calorimeter. If we take that, which is the energy that was stolen by the calorimeter, and divide it by the temperature range over which the calorimeter went, so we're going to have a different delta T here, we're going to end up getting our next calculation, our delta T for this calculation. When you divide, you're going to get energy per degree Celsius, so joules per degree Celsius here, and we've now calibrated our calorimeter. Now, quick reminder, remember the average of these two is going to be our T average, and T initial is going to be the, oops, I'm sorry, now I'm on to data table 2. When we mix two liquids together that are slightly different in temperature, we're going to assume that the average of those two temperatures will give us our T initial. That's different than first reaction. Remember, when we had our cold water, and I apologize for the announcements that are happening, when we had our cold water, the cold water was our T initial. Now, to continue on here into part 2 of the calculations, now we're going to be actually looking at our Q equals mc delta T of our reactions. And remember, we're going to be fixing the energies. So here is where we would use our data and our T mix to get the energy of the reaction. And then over that temperature range, we can find out how much the calorimeter stole to get a better look at what our Q of reaction was. And remember, for part 2, it says that the densities of our solution, because it's no longer pure water, you should use 1.03. And for the specific heat, we're still using the 4.18 like we did before. And then in the last one, in number 3, remember if you calculate the moles of NaOH or HCl or NH, notice they're all 1 to 1 to 1 to 1 stoichiometry. So if we calculate the moles of any of these, that would give us the amount of moles that we had. So we're going to take our answer in number 2, convert it to kilojoules, find out how many moles we've got, and divide, and we get energy in kilojoules per mole for our reaction. Now, last thing would be to finish up the calculations where we're verifying Hess's law. Don't forget in number 1, it says write the thermochemical equation, which means we need to include the substances and their states and the energy. Now, you can include it in the actual reaction if you so wish, or you can write it as a heat of reaction. Just remember, negative it's going to be on the product side, positive it's going to be on the reactant side. Do that for the 2 reactions. And then in 2, you're going to end up showing how 1 plus the opposite of 2 does equals what, because that should be what we get for number 3. So remember, here in number 2, we're actually doing that 1 plus the opposite of 2. And it's really supposed to ending up equaling what was in 3. So that would be our actual measured value. So in part 2, question number 3 for the third reaction, that's where we're getting our measured value. And then right here, these are going to come from what we got there. And we can calculate then the percent difference between the two. And that ends the discussion that I wanted to hit over different parts of the lab. Thank you.